right, you find that is, I mean, any internet issue. Okay. So is my screen visible?
Yes, sir. Yes, sir. It is visual.
Yeah, it's perfectly visible, right? I mean, there is no
Uh,
blurring and all. Yeah.
no, sir. It is clear.
Okay. Okay. Thank you. Thank you. I'll make it full screen.
Yes.
Yeah. So good evening, everyone. Welcome to the last session of day 11. Right. And in this particular session, I'll be focusing on retinal fundus image analysis and how deep learning algorithms are nowadays applied to analyze the fundus images, basically retinal fundus images, to detect several eye conditions or ophthalmic conditions. And here is the outline of this particular session, where I'll be touching upon initially what do you mean by fundus image, how it looks like, how it is captured, and why deep learning. Why deep learning? Already we all know that, right? We've seen its advantages over since last 10, 11 days, right? Advantages over traditional approaches. And I'll be focusing on only two types of eye conditions today. One is like glaucoma and one is diabetic retinopathy, although there are various eye conditions, right, which we work on. Even there are several others exist in the literature. So mostly I'll be focusing on two type of eye disease. One is glaucoma and one is diabetic retinopathy. A very common disease, severe eye disease. And we'll see how it is currently being detected and what are the advantages of deep learning based algorithms. We have seen the advantages of attention mechanisms also we will see here. And what are the different types of tasks, right, which we can have, right, in the domain of fundus image analysis. And at the end, I'll talk about few research directions, right? So as we all know that the total number of cases, right? Eye disease cases are really high, right? I mean, if you look at the current scenario, right? So there's statistics in 2019 by WHO that there are 418 million people who suffer from eye disease, right? And such kind of disease include glaucoma, diabetic retinopathy, age-related macular degeneration, cataract, myopia, and several other type diseases. In India, if you look at the most common eye disease are diabetic retinopathy, cataract, glaucoma, right? So there are some certain issues. I mean, I will talk about it while I will describing discussing this glaucoma, right? So the patients actually with the eye disease, right, are initially basically when they are in the early stage, they are unaware basically about their conditions, initial conditions, because some of the diseases are asymptomatic, right, during the initial times. So we'll talk about it later on. And that's why what is more important here, because the case is rising exponentially, the number of cases are rising exponentially. What is most important here is to detect, right, this kind of eye conditions at an early stage. If you can detect it and if you can treat, you can provide treatment at an early stage, so probably you can save the vision, right? So that is what is our main goal, how to detect I mean, this kind of disease at an early stage. Yeah, so if you look at the anatomy of the eye, which we have seen from our school level science book, right? I mean, a science subject that yes, this is the anatomy of the human eye, where you will find yes, this is where I mean you can see the iris, there's a pupil, there's a lens everywhere, right? But when we talk about fundus, what do you mean by fundus? When I say fundus, it is nothing but the base part of the base part of the inside of the eye, right? Where you will find retina, you will find macula, you will find the retinal blood vessels, and also optic nerve, vein, and there are so many things. And this is the optical, the optic nerve is very, very important for certain kind of disease, right? Which is known as glaucoma disease. We'll discuss about it, right? And retinal blood vessels are very, very important because these are such vessels which carry bloods, you can say oxygens or nutrients, and provide it to the retinal, right, or inner retinal layer kind of things. So very, very important for us, right, to understand these kind of things. And why do I mean there are is there any other imaging technologies like we have seen last 10 over the last 10 11 days that there are multiple types of medical imaging modalities such as x-ray, ct scan, and so many, right? So what are the different types of imaging modalities we have for diagnosis of the eye disease? Yes, there are different type of modalities are available in this case, which are nothing but like OCT is one of the very popular kind of imaging technology. There is fluorescein angiography that is also very popular. But among all this kind of eye scans, or you can say medical imaging modalities, fundus image is very popular and extensively used by the ophthalmologist. Why? Because it is non-invasive and it is cost effective as well. So that is why it is very much suitable for large scale screening of the eye disease, right? And there are also some portable devices for fundus images which are available now. Even there are certain cameras, fundus cameras, which you can easily equip with your mobile camera, and you can just take the photography of the backside of the eye, which is nothing but the fundus image. Right. So this is how actually the fundus image finally looks like when it is captured through a fundus camera. And if you look at this particular image, you will find there are certain blood vessels here. Blood vessels are clearly visible, you can see. And at the same time, you will find there are certain pathological regions, and these pathological regions basically are nothing but the indicators for certain eye disease. Right. We'll talk about it whether one type of disease at a time, right, can happen with one particular patient, or multiple types of disease can also have, I mean one patient can have or not, right? So these are very interesting things of which we discussed with some of the ophthalmologists in our country, and then we decided to solve few problems based on that, right? So if you look at the pathological regions, this is how actually the optic corp and disc looks like, very important for the diagnosis of glaucoma, right? And this is how actually the optic nerve, right? When you capture the fundus image of the optic nerve, it will look like this. One is optic disc, and there are like two concentric circles, right? Optic, the outer side is disc, and the inner one is optic corp, right? We'll see, how this glaucoma is currently being detected manually by the ophthalmologist. There are, if you look at certain other regions here, pathology regions like hemorrhages and soft exudates, hard exudates, microaneurysms, right? And these are all blood, retinal vessels, right? So these microaneurysm, hemorrhages, soft exudates, hard exudates are very important pathological indicators for or clinical markers for the diagnosis of diabetic retinopathy. We will see right later on. But this is how actually a fundus image looks like. Sometimes for a particular patients you can have two fundus images for right eye, for left eye. Right. We'll see how to deal with those kind of things later on. But among all the medical imaging, basically eye scans, right? Fundus image is pretty preferable. Why? Because of its non-invasive nature and cost-effective nature. Fine. Yeah. So this is how actually the fundus photography and sometimes some of the portable fundus photography camera looks like, right? So it's a very easy to capture the photos. You can see over here. So there are also the fundus photography of infancy. We can now, if you also want, you can just take the fundus photography of the children as well, the babies, and the fundus photography for cataract patients. So the characteristics of the fundus image in the pathological regions for each of these disease, right? Eye disease is very different. That also we need to understand, right? So we have at least got little bit. We have little bit of experience now, so we can at least tell yes what kind of disease that is there in this fundus image. But still, there are cases which we cannot write. We need the help of the ophthalmologist there. So if I just categorize the problem, the problems of retinal image analysis, which can be broadly categorized into three types: classification, segmentation, and synthesis. So classification is very simple. As you know, either you have to classify whether the fundus image belongs to, let's say, for example, glaucoma or non-glaucoma, like that. Segmentation is, let's say, optic curve and disc is very important, as I mentioned, for glaucoma diagnosis. So you have to segment those regions appropriately. You need to highlight these regions basically where there is optic disc, where there is optic curve in the image, right? And that is what is partitioning an image, and this is basically region of interest, and this can be considered as a classification problem, right? And again, for any type of eye disease, you can have classification problem, you can have segmentation problem, right? We will discuss it later on. Even for the diabetic retinopathy, also we can have grading problems. We can also have segmentation problems. Synthesis is quite interesting here in this case because, as you all know, that yes, number of samples are quite limited in these cases compared to the natural images. So can we synthesize this kind of images? Is it possible to synthesize? We have also done a little bit of work on this. I mean, how to apply these deep generative models nowadays to synthesize the fundus images, and to just have a robust training of the models, because the number of images are very less. And what we can do, that we can just synthesize the high resolution fundus photography images with the help of deep generative models, and just use them to train the model, right? That is what is synthesis. We will see, right? There are a couple of works which I mean, because the work is still in the immature stage, so there are a couple of works that needs to be done in future. I mean, when coming to deep learning, of course, I mean, because nowadays nobody is interested in applying this, machine learning based algorithms. You all know that why we've seen its importance over the traditional machine learning approaches, where you need to extract the features manually, apply the classification algorithms. You need to choose which type of features. You need to choose again the best type of classifiers, and again, it's all right dependent on the expertise which you have. So we know the advantages of deep learning. I'm just keeping the slide. And if you look at one particular graph which I've taken from one paper. I mean, just where I just got this information. The number of papers that was published in 2019, right? So I just collected from a world paper. So from 2012 to 2019, if you just look at the graph, the number of papers published in the field of fundus image analysis, it is growing exponentially, right? In 2019, if you look at 912 papers were published using deep learning algorithms using fundus. I mean, per fundus image analysis, basically, right? So that means it's really exponential. And also, if you look at the number of papers per task, that means whether the papers focused on diabetic retinopathy, whether the papers focused on glaucoma, cataracts, age-related macular degenerations, there's a couple of problem statements here you can see, right? So whether it is retinal vessel segmentations and all, right? Vessel identifications, very, very important for certain diseases. So if you just look at this graph, you will find, yes, the number of papers, I mean, the contributes. I mean, if you can just see the percentage which contributes to particular DR category is 16.8, for glaucoma it is only 9.8, right? So there are many, I mean, you can say there are still a lot of work to be done. We'll see what is left and what is the current demand, right? By the ophthalmologist in the for the real time screening and all. So now I can also show you one interesting thing here. Like if you look at this, the percentage for this multiple disease, which is very, very less. So I'll talk about it later on. What do you mean by this, multiple disease and why it is important nowadays? It is like, can we have a unified model, right? Instead of developing models for different disease individually, like separate models for different diseases, can we have a single model which can, right, solver which can detect all possible types of disease? And there's a possibility that one patient may have multiple eye conditions at a time, which is very, very difficult, because if you are, let's say, designing one particular let's say model which is dedicated for diabetic retinopathy, classification of diabetic retinopathy detection, basically, and that cannot help you in detecting glaucoma, right? Because that is specifically designed for diabetic retinopathy. So now my question, if the person is, let's say, having both the conditions, diabetic retinopathy and cataract together, so you cannot, I mean, your model is now not able to detect, right, both the things at a time, because it can either detect diabetic retinopathy or cataract, because you are having two separate models, one for diabetic retinopathy and one for cataract. So what we want to design such a model which can detect multiple conditions at a time. That is what is our goal here, right? I mean, it's very, very important problem statement, and very limited work has been done till date. So coming directly to the problem statement, which is glaucoma, as I mentioned, one of the leading cause of blindness, right, across the globe, and the number of patients, like number of individuals suffering from glaucoma is really high, right? And number of blindness cases are also, I mean, comparatively very high compared to the other, because this kind of disease is irreversible. This glaucoma is an irreversible disease, right? So it is very, very important to detect glaucoma at an early stage, because the early stage patients, right, uh, are unaware of their conditions, and because it is asymptomatic kind of thing. Fine. So, as I mentioned that yes, glaucoma is one of the leading cause of blindness, and it basically leads to optic nerve damage. So, I've shown you what is optic nerve. It is connected to the brain, and if it got damaged, and then the person becomes blind, right? So, I mean, basically, this results in irreversible and permanent vision loss. So you can see the impact of the vision loss, the impact of the vision loss, right, from this figure. So I mean, this is just a normal one. I mean, if a normal person is, you can see the scene like this. But if the person is suffering from glaucoma, and if he is in early stage, then this is how actually the impact of the vision loss slowly, and at an advanced stage, this will get blackout, and that means the person will be blind, right? So very important to early detect this kind of disease, at least to save the vision, right? And if you look at the number of if you look at the statistics, around 64.3 million individuals aged 40 to 80 years have glaucoma in 2013, and it is expected to affect around 113 million people by 2040. So that's why doctors used to always recommend to go for regular eye checkups and check, right? And there are also certain symptoms that ophthalmologists can better suggest that, I mean, why glaucoma, what are the symptoms, and you can what are the possibilities that glaucoma may happen, and why basically this is happening. It is just happening because of the excessive pressure inside the eye, right? So what do you mean by this pressure here? So if you just look at this anatomy of the eye for the two different cases, one is for healthy eye and one is for eye with glaucoma, right? So basically, what happens? There is a fluid kind of thing which is always produced in the human eye, which is like aqueous humor fluid, which is continuously actually produced inside this eye. But sometimes this fluid gets blocked, right, and it cannot drain out. That is why, and I mean, if it is blocked and it is not drained properly, and this creates pressures inside the eye, and because of which there can be some damage to the optic nerve. You can see over here. So this is a healthy optic nerve. You can't see any damage to here, but you can see some damage over here, and because of this damage to this optic nerve, right, and the person actually suffers from the glaucoma disease. So this is how actually the glaucoma can be detected, but this can be detected with the help of different imaging technologies or different imaging modalities, and one of the modalities is fundus imaging, right, where you can take just the backside of the. So easily you can detect this glaucoma with the help of fundus images. If the if the severity or if the damage to the optic nerve is significant, right? If it is less, then it is sometimes even difficult for the ophthalmologist, right, to detect glaucoma. So how it basically looks like when you capture the fundus image, I've shown you earlier, right? Now it is just become like this optic disc and optic curve. So what are the procedures or standard procedures that ophthalmologists used to follow in clinics to identify glaucoma? Yes, it is. There are two clinical metrics actually, which are like considered as a gold standard here. One is COP to disc ratio. You know what do you mean by COP? I have already shown you, and you know what do you mean by disc. And they are using one metric known as COP to disc ratio. And there is one more also important. You can say the clinical markers they used to use, which is a retinal nerve fiber layer defect, right? And based on the thinning of this particular layer, right, RNFL layer, so they used to identify whether the person is at early stage or advanced stage, like that. So if you just try to see, I mean, how there is a change in the fundus image for a glaucoma patient compared to the normal one or the healthy one. So this is how actually it looks like. If you just compare these two pictures, this fundus image is nothing but it's a normal eye, and this fundus image basically tells us it's a glaucomatous eye, right? So now if you just look at, because as it basically damages the optic nerve, right? In our case, it is optic curve and optic disc. If you look at here, and then what they are using is they are just computing manually the CDR value, right? What is the CDR value here? That is curve to disc ratio, as I mentioned, right? So the outer circle is nothing but here the optic disc, and this inner one is like optic curve, and just take the diameter and divide this with this, and then if the ratio is greater than zero point 0.5, then they used to claim that yes, it belongs to early stage glaucoma, and if it is beyond zero point 0.8, then it is like advanced stage glaucoma, like that, right? So I mean, this is this kind of examination or assessment is purely manual and very difficult. For there are a couple of early methods. If you go through the literature, you will find where initially they used to segment the optic curve and disc region, and then manually try to find out the CDR values, right? And based on the CDR value, they can decide that whether a person belong to early stage glaucoma or advanced stage glaucoma, and kind of that. Right. So now you can see, if you take just the ratio over here and here, so this the ratio in this case will be definitely higher, and this is how actually you can identify, right? So if there is a damage to this optic nerve, then the size will definitely get, the size of the optic disc will be enlarger, and it will definitely get damaged. You will get to know about it, right? So this is how actually the ophthalmologist used to manually access or manually diagnose whether the patient is having glaucoma or not, and these are certain clinical markers they used to use while detecting the glaucoma or while checking the glaucoma patients and all. Yes, there are different types of tasks, right? If I come to only glaucoma glaucoma detection. So it can be again divided into two subtasks, like glaucoma classification and glaucoma, optic curve and optic disc segmentation. Again, among this glaucoma classification, there can be binary classification, there can be multi-class classification. Binary means whether this is like a binary class, right? This is a binary classification problem where you'll be given a set of images, you will design a model, and your model will only tell whether it belongs to normal category or healthy eye category or glaucomatous eye category. That's a binary problem. But as we all know that yes, glaucoma stages are also very important for us. So we can also identify, I mean, at which stage the patient is at, right? So that also we can do. So if you just go through the literature, you will find that initial methods, as I mentioned, were like segmentation-based methods where they were segmenting the optic disc and curve, followed by some of the measurement of the clinical values like CDR values to detect glaucoma. But later, when these machine learning methods came in the picture, so they, they used to extract the handcrafted features, like the features we have discussed earlier, like the overlay features, the GLCM features, and some texture-based features can be extracted from these fundus images, and then those features can be passed to the standard classifiers. And there are a couple of works on this in the literature. Basically, if you go through the old literature, you will find this kind of works. But as you all know that yes, with the advent of these deep learning algorithms and its advantages, people have also tried applying convolutional neural networks, especially to detect glaucoma. And but there are also certain disadvantages or limitations while applying this convolutional neural network, traditional convolutional neural network. And to detect this glaucoma, CNNs, the traditional CNNs fail to capture the minute variations, right? And there are also a couple of methods you will find in the literature which are mainly focused on solving binary classification problem, but which cannot decide the stages of the glaucoma. That's what we all know, and you will find very limited papers on the multi-stage glaucoma classification, basically through the fundus images, right? Yes, when I say multi-stage glaucoma classification, what does it mean? That you have to, given a fundus image, you have to classify this image into certain categories like healthy, early stage, advanced. There are also moderate stage and few more stages which you can include, but it is very difficult to get those kind of data sets, right? And because the patients usually, when I mean the doctors used to say, the patients usually come at the later stages, right? So sometimes it is difficult to create those kind of data sets. I mean, maybe having some images for moderate category or even some other categories. Right. So mostly, I mean, these are the three categories which are used, like normal, early stage, and advanced stage. Right. But you will but while solving this problem, you will find a lot of challenges. Right. So what are those challenges? Like while solving a binary classifications, you will find comparatively the challenge is not that significant, but here the challenge is even more significant. Why? Because there's a possibility that you may have some large interstate similarity, and it happens right all the time that you will find large interstate similarities. You will find there are some similarities among the stages, the similarity of early with the normal category, early with the advanced categories. Here for simplicity I have chosen three extreme conditions, I mean three samples from the extreme conditions of early stage and advanced stage, but there are also few samples which I will showcase to you, so you cannot able to identify directly or by looking at the image, right? Directly you cannot predict that whether it is whether this glaucoma or basically whether this fundus image belongs to early stage or advanced stage, right? It's very very difficult to identify. There are certain redundant informations because for glaucoma, as we all know, that yes, the most important part is this optic corp and optic disc, and there are also some parts related to this like retinal nor fiber layer defect, right? That the I mean except those two markers, the other regions are like redundant for these cases, right? And then you will also find sometimes there are the lesson size, shape, right? Color sometimes varies, right? It is very, very difficult to find those variations, right? Because those are minute in nature. So how to just identify those kind of things? So we have done few works since last couple of years, like 4 or 5 years. We have been working on this problem for solving glaucoma classification. I mean, and then optic op, optic disc segmentation, and also we have been working on some other kind of disease like eye disease, basically. And here are the four case studies I would like to discuss with you. Right, one is like glaucoma detection using fundus images, which is in early days we used to solve this binary classification problem. Then when we discussed with the doctors, then doctor said why not to design a model which can also detect different stages, which are very very important. Right, so the goal is of course to detect early detect the disease, and because we know that this can be easily used in the underserved regions. I mean if you can design something and CAD kind of systems and which can be easily integrated into the mobile system, and which can be easily deployed on the edge devices, and through the help of those fundus cameras, right? You can easily capture these photos, and you can process those photos with the help of your algorithms, and at least you can suggest or recommend the patients, right, who are let's say where the clinical settings are not that much better. So what we can do is we can just suggest them to just visit to the nearest eye hospitals as soon as possible, because with the model is saying that you are suspected, right? So that's what is the major goal here, right? So as I mentioned that we have done some work initially on binary classification. So here is some of the works which I've done on binary classification. That is very simple, like given a set of images. Uh, Given a set of your fundus images, your task is to build a model, and then classify those fundus images into two categories, that is normal and glaucoma, right? I've chosen two extreme cases, as I mentioned, where you can easily see that how this optic nerve size, right, is different from the optic curve, and this size is different from this optic curve and disc which is there in the normal images, right? So you can easily find out that is the CDR value is really high in these two cases compared to this normal values. But yes, there are a few cases where you will definitely get confused. So that is why we want, right? And there can be some even miss rate over here. So that is why it is better to have some type of deep learning kind of model which can extract those or patterns of which are minute, right? So we have developed something called as a channel coupled dual attention based multi-scale convolutional neural network, and this is how actually the network looks like. So if you just look at this architecture, it contains initially some stem layers, like few convolutional layers and pooling layers to reduce the dimensions of the feature map. And then we have applied a multi-scale MFR block, basically multi-scale feature representation block. The goal was to cover the is to learn the features at different scales by enlarging the receptive field, but not by using the high size or large size filters like 3 cross 3, 5 cross 5, 7 cross, not like that. The same thing has been implemented with the help of only 3 cross 3 and 1 cross 1 filters, so that the number of parameters, right, will be reduced. So after every this multi scale feature representation block, which basically helps in extracting the features at different scales, we have proposed one attention module again with the help of the channel attention, the spatial attentions, which we have already seen, right? And there is one more, channel shuffle unit which has been introduced over here just to have a better feature flow within the network, right? So after extraction of the multi-scale features, it always pass through these attention modules, right, to focus on the important part and ignore the irrelevant part. So if you just look at this particular channel attention block, it looks pretty different from the channel attention block which I've shown in case of squeeze and excitation, where you will only find this one path, right? The weights of the channels were computed using this one path, but here it has been computed using two different paths, using global average pooling as well as global max pooling, right? And then both of the weights are here averaged basically, and then finally you will get no, so you can say the final set of weights which is multiplied with the input feature map, right? And then what you are getting is a channel wise feature attention map, right? So similarly you can see the similar kind of operations we have also applied in case of spatial attention block, where we are not only applying the cross channel average pooling, right, to get this two-dimensional feature, I mean two-dimensional attention scores or attention weights. We are also applying cross-channel max pooling to get these attention weights. And after getting these two attention weights, because ultimately we need one attention weight, so we are just applying the average operations among these two to get the final average weights, and then those final average weights will be multiplied with this, and this helps in improving the performance as well, right? So here is the comparison of our proposed approach with the state-of-the-art convolutional neural network model, starting from BGG to mobile net, dense net, and all. And also there's a comparison in terms of parameters and size. Right, you can see the number of parameters required by the proposed model, CDAM net, and this MFR net is this. This is the architecture without the attention model. Right, without the attention model, you can see the number of the number of parameters is relatively low, and the size is also relatively low. So while introducing this attention mechanisms, one thing we need to remember, because we are also using some convolution operations over here, there are some learnable weights inside these blocks, and these blocks sometimes introduced, right, parameters, but we need to also take care of that how much parameters it basically it helps in improving, right? So it will, I mean, while requiring few additional parameters, it gives better performance, right, compared to the traditional approach. That's what also we need to take care of, that sometimes there are some attention mechanisms which also helps, which basically causes um, parameter, you can say the large number of parameters, right, inside the models, which is very difficult sometimes to combine these attention models throughout the architecture, right, because it introduces a lot of parameters, right? So here is again the comparison of the proposed attention mechanism with the other approaches. You can see, right? So it is giving relatively better results in terms of different types of performance metrics, right? Yeah, it's just an example. I mean, this comparison with the state-of-the-art glaucoma detection methods. Some of the glaucoma detection methods, if you look at the early approaches, they were like machine learning based, right? Texture features followed by random forest classifiers, cross entropy based features, and EWT based features followed by a least square support vector machine. So these are all traditional approaches, right? So these are not end-to-end learnable. A few methods which are end-to-end learnable. That's what I've seen. So coming to some of the work which we have done on multi-stage glaucoma classification, which is a very relevant topic because our goal is to identify the multiple stages of glaucoma here. So we have also proposed few attention-based architectures, as I mentioned earlier. So this is one of the architecture which we have proposed, and the paper got published in IEEE Transactional Instrumentation and Measurement in the year 2023. So where our goal was to initially learn the features, I mean the local features, high level features from the any backbone network like convolutional neural network. And then after getting on the high level feature map, so we are just passing this feature map to a cascaded attention module, which also contains channel attention, spatial attention. But if you look at this channel attention, it is pretty different from the traditional channel attention which you have seen. So it is the name itself is known as triplet channel attention. You can see there are three different paths. So basically, what we do inside this channel attention block is we always try to find out or capture the feature dependencies right along the channel dimension. And here in the spatial, we are also doing the same thing. We're trying to find out the feature dependencies or feature interactions right along the spatial dimensions or positions. So, I mean, what we've seen that yes, one-dimensional channel attention creates, gives us 1D kind of weights, and we are multiplying with all the channels of the feature map, and then we are getting, a channel-based attention feature map where the important channels are highlighted, and the rest other channels which are not important, which they are ignored. So then we thought of why not to combine the interactions, the channel interactions with the other two things, like the channel interactions with basically, it is a cross-dimension interactions, right? So always feature interactions are happening either in channel dimension or in spatial dimension. So I need to have a cross dimensions, right? Basically, it is just channel with height and channel with width, right? So there are two basically, these are like also channel-based attention, but where we are trying to find out the cross-channel attention and cross-channel relationship with width and with height. And that's why if you look at this particular if you look at this particular channel or attention score, which is 2D in nature compared to the traditional one, which is 1D in nature, right? So then finally we just combine them together, and then we'll be having a detailed, or you can say the comprehensive feature interactions along the channel dimension, followed by the traditional spatial attentions. And this also helps in increasing the performance, right, significantly compared to the traditional attention mechanisms which we have seen, like squeeze and excitation, CBAM, global context, global attention block, triplet attention block, and so many. Right? You can see the number of parameters if you compare with the others is little bit higher, of course, little bit higher, but it is, it's very marginal, you can see, right? But the accuracy or the performance is relatively better compared to the other attention mechanisms. Fine. So another contribution which we have recently made, or where we have developed, a fuzzy joint attention guided network. So I don't know how many of you have worked with fuzzy. So it is just the concept we have taken from the fuzzy logic. So why do we need actually fuzzy here? Because what we have observed even after applying this kind of attention block which I just now discussed, still there are some regions in the fundus images which are uncertain, right? Which are ambiguous. So very, very difficult. Those ambiguous informations are creating confusions in the networks, and it basically leads to some misclassifications among the stages, right? So you need those kind of, you need those kind of one architecture which will just remove this kind of uncertainty information, so which will help us in removing this basically ambiguity information which is present in these fundus images. So then we come up with this idea that where again, if you look at the backbone, we have kept the similar, that we are taking features initially from a backbone. This can be vision transformer backbone. This can be a convolutional neural network backbone. So followed by an attention module. We have of course introduced a fuzzy layer, but we have also introduced how to incorporate the local channel attention as well as global channel attention. In my attention session, in my lecture, I already mentioned the role of local attention blocks and the role of global attention blocks. As we all know, that global attentions are very, very important, right, for extracting the global contextual informations from the image, along with the local will help us in getting the more detailed contextual information, right? So but again, this local and the global attention can be done in different dimensions, or can be done either in channel dimension or in spatial dimension, right? So if you just look at here, so if you look at this connection, so local channel attentions is followed by local global channel attention. So similarly, in another path, you will find local spatial attention is followed by global spatial attentions, right? So in every path is followed by a fuzzy layer, right? If you look at, and this particular module is known as the fuzzy joint attention module. I'll show you how it helps in discriminating or in learning better feature representations compared to the traditional one. and how this fuzzy is also helping, right, in discriminating or having a better feature representations, right? Because what we've observed, there's a large interclass similarities, right? And so how to just remove those kind of similarities to some extent. So this how this fuzzy is helping us here. So this is how actually the fuzzy joint attention module looks like, as I mentioned. So this is the local channel attention which we have seen earlier. This local spatial attention which we have seen earlier, which is combined with a global spatial attention, which is a kind of self attention. This is self attention which we have discussed earlier, right? And but I also mentioned the self attention can be made along the spatial dimension as well as the channel dimensions. So this is what we have done here. So the this is this the channel, I mean, you can say the self attention in the spatial dimension. I mean, this is known as global spatial dimensions, where you are trying to find out the pairwise relationships, right, among the pixels or in the feature map. So similarly, I mean, how every pixel or how every pixel in a feature map is related to every other pixels. Yes, the same, the rules are same, whatever you have seen. Like there is a query projection, there is a key projection, there is a value projections, the key and query gets multiplied. There is a softmax operations over here, and what you are getting finally, attention weight saving size SW plus SW, and then it gets multiplied to the value to get the final one. So similarly, you can also see over here, as I mentioned earlier, that you can also find the global contextual relationship or feature dependencies along the channel dimensions. But in that case, the sizes of the size of the attention score will be C cross C in place of SW cross SW. So these are common things, right? So after getting the final feature map, after applying this local channel followed by local spatial followed by global channel, so you'll get the attention map, right? Final attention feature map, right? So these are like refined feature maps. So this feature map may contain again some of the redundant informations like ambiguity information, or you can say uncertain information. So how to just deal with those type of information? So for that we have introduced fuzzy layers, right, in both the paths. So this fuzzy layer is nothing but where we are directly using three types of member functions, not only Gaussian member function but also sigmoidal or trapezoidal member functions, which will help us in giving us fuzzy map. And finally, the fuzzy maps which we are obtaining from this type of uh, you can say the membership functions are then we just combine them together using or operation, not and operations, or operations, like in fuzzy just to find out the maximum values from this, right? And then finally, we are combining the fuzzy maps, whatever we have obtained from the first path and the second path here, right? And then we are just combining it. And finally, what we are getting is a refined feature maps, right? And this basically helps us in separating, right? This is the visualization results of the feature embedding, right? The kind of feature we have learned. If you see this particular you can see the cluster, right, of three different classes. These are like samples uh, which are represented in three different clusters, and where you can see the separability among the classes is very low if you are considering only the backbone architecture, which is DensNet 169, right? So and there are also certain samples of this class you will find over here. There are certain samples of this class you will find over here with only the local and global attention without the fuzzy layer. Some of the reviewer asked us to, I mean, just uh, provide us some of the visualization result on how visualization results, how this fuzzy layer is helping us and in improving the feature representations. Right? This is why actually, I mean, we have just tried to find out this feature embeddings with the help of TSNE, right? Stochastic neighborhood embedding approach, basically. And if you just look at this particular graph, where you will find the clusters, right? It is also forming three clusters, and the results are a little bit better. There is a better separation among the three classes, and I mean, you can see there are few samples which are right of, let's say, this category, early category, that basically comes to advanced category, like that. Fine. So, but after applying this fuzzy layer, now if you look at this particular graph, the last graph over here, right? So the clusters are well separated, right? The clusters are well separated, and then the distance, basically the distance among the clusters are high, and there also if you look at the intra class distance is also less. right? So this is how actually the fuzzy is. That means this is how actually we plan to remove the ambiguity informations from the feature maps and how it helps in improving the feature representations. Fine. And there are some quantitative results where you can just go through our paper here and which is published in IEEE Transactions on Fuzzy Systems. This work is with my PhD student Dipankar, right? So yeah, there are a couple of interesting results which we have got, and there are a lot of ablation studies also we made to just check whether this local and global attentions are important together, or whether global attention only is giving us good results like that. So we'll find some interesting results, right? So in our paper, so you just go through the paper for more details. And as I mentioned that yes, there are certain other problem statements which also, I mean, which if you want you can solve, right? I mean, you will find in the literature there are a couple of other similar problems, right? And this is was just the example of right, like optic cop and optic disc and cop segmentation problem. It is a segmentation problem where your task is to given an image. You need to highlight the boundaries and the regions, right, of the optic disk as well as optic corp, right? This is, let's say, these are nothing but the ground truth, I mean, provided by the ophthalmologist, and these are some of the results, right, obtained by the deep learning models, right? And based on this, you can just check how your deep learning model is performing better compared to the already available, or you can say the existing models available in the literature, right? So coming to another type of problem. Statement, or you can say another type of eye disease, which is diabetic retinopathy, right? Which is a very, most common sight-threatening eye conditions, and it is basically caused due to diabetes. And we know how many, people or how many patients are suffering from diabetes, right? It is really high. It is 425 million, and it may rise to 693 million by 2045. And this is according to International Diabetes Federation estimates, right? So that it may rise to 693 million, which is a huge number by 2045. One of the, basically, I mean, we're talking about the number of diabetes cases, right? Number of diabetes cases, not the diabetic retinopathy. Diabetic retinopathy is certain eye condition caused due to diabetes, right? And there's a possibility. See, one of the three individuals who are suffering from diabetes is estimated to have some form of diabetic retinopathy, and 1 in 10 is prone to vision threatening. So that means the number of diabetic retinopathy cases are somewhat related to the number of diabetes cases, right? Because one out of three individuals, all right, is estimated to have some form of diabetic retinopathy. So that's why it is very, very important, right? That's why doctors used to always suggest the diabetes patients to go for regular eye checkups. Right? They may suffer from diabetic retinopathy issues, which is very, very, right, important to detect at an early stage. So the diabetic retinopathies, again, as I mentioned, there are a couple of medical imaging modalities, right, which can be used to detect diabetic retinopathy. But fundus imaging is one of the most, extensively used medical imaging modalities to detect diabetic retinopathies. And the pathology, the clinical indicators are something very, different. The way which previously we have seen, yes, the optic curve and optic disc is very, very important, right, to detect glaucoma. But in this case, the clinical markers, all right, or the indicators are very different. So this one is a fundus image, as you all know, right? And here are the four pathology, or you can say lesion, pathology regions for which actually the person is suffering from diabetic retinopathy. So what are those? One is microaneurysm, one is hemorrhage, one is hard exudate, and one is soft exudate. So hard exudate is sometimes easier to identify, because if you look at these patterns and the color, the textures, which looks very different from the background pixels. But if you look, hemorrhage is also somewhat sometimes easier to identify. But if you look at microaneurysm and soft exudates, it has lot of similarities. The patterns, the textures is lot of similarities with the boundary pixels, or you can say the surrounding pixels, or right. So it is sometimes very, very difficult to identify, right? Through the naked eye. So then, how to identify this? Because the presence of these may lead to diabetic retinopathy. So if somebody is missed, right? I mean, with this microaneurysm in soft tissue rate, so it is very, very difficult to identify whether the person is having diabetic retinopathy or not. So how to identify this and what are the problem statements, right, of which we are having in this case? Again, there are two problem statements. One is like how to segment all those regions, a very, very difficult problem. And at the same time, how to grade the diabetic retinopathy. Can have different types of gradings, right? No diabetic retinopathy, proliferative diabetic retinopathy. So it can have five different grades like that. So that's the classification problem. And we can have both classification problem as well as segmentation problems over here. Right. For classification, you may use the classification models. For segmentation, you can go for the segmentation models, right? So I'll show you one interesting, example. I mean, basically interesting table where basically you can see the summary of a particular challenge, right? I mean, basically this is known as a leaderboard nowadays. People are talking about, right? So there was a challenge in 2020 where I mean, you all know what you mean by challenge, where the organizers used to provide some sort of training images. Based on the training images, you have to design your model, and then you have to submit your model to the organizer. The organizer will test your model on the test data, and then finally they will declare the winner. But initially, as I mentioned, initially people have started with segmenting these regions or these pathological regions separately. I mean, it's individual. What does it mean? That for hard extruded, they'll be having one model. For soft extruded, they'll be having another model like that. But current trend is to design a single model to detect all the four kind of pathological regions. So it's just even more difficult to identify, right? So I mean, if you just look at this particular image, and here are some of the ground truths. Just look at the figure number B, C, D, and E. Just forget about F, because which basically tells us the optic disc. We are not interested in this case. We are interested in identifying this microaneurysm, hard exudate, soft exudate, right, and hemorrhage. So these are the four cases, right? So like microaneurysm, right? Here you can see the hemorrhages over here, right? And these are like right now binary, right? Binary segmentation problem, because there are only two classes. Either it belongs to microaneurysm or it belongs to this. Why this problem is so challenging? Can you tell me why this problem is so challenging? It's very, very difficult to identify. See, a single pixel sometimes will belong to microaneurysm category, right? It is not like a tumor where you will find it. Let's say in case of optic disc, you see, right? The size is pretty, larger compared to this size of the lesions or the size of the pathological regions. The size of the pathological regions are very small, irregular. The shape are, I mean, the say there are a lot of variations in the shape and size. You can see over here. So that is why the segmentation of the diabetic retinopathy lesions are very, very difficult compared to others. So we must have some robust models which can detect or identify this kind of lesions where the shape, size, and it is distributed all over the image. Very, very difficult, right? So as I mentioned, but when the goal is like to detect all those, right, all these lesions in one go, so it is very, very, even if it is more difficult, right? Because at that time you will be having five different classes, right? Four, background. I have discussed already, right? It earlier that how many layers you'll be having in the final layer of the unit, or some variants of the unit architectures, right? So I mean, yeah, I was just showing this table to you. I just wanted to inform you something, right? This is these are taken from one paper from 2020, right? I mean, at that time also, I just wanted to show you that how this unit architecture and similar kind of convolutional neural network architecture was so popular at that time and became the winner, right, of their challenge. So as I mentioned, there are four independent segmentation problems, and every time you will there are four team members, right, whose name has been listed here. Like these are four. Like the first one is the winner, the second, first runners up, second runners up, like that for all these four cases. And then they have computed area under the precision curve. For in case of microaneurysm, the winner was having area under the curve around 0.5. For hemorrhages, it is 0.68. For soft oxidate, it is 0.69. For hard oxidate, it is 0.88. Hard oxidate, I have already shown you that it is conditions. So that's why the result by the best method was pretty good compared to others. And now if you look at the approach here, just look at the approach. So every time you will be having Yeah, I think I got disconnected. Yeah, Dr. Vikas. So can you see? Yeah, is my screen
Yes, sir. It is
visible?
visible, sir.
Yeah, I
Yes,
got
sir.
disconnected. I was in this slide or this
Uh,
slide? Yeah, this slide, right?
yes, sir. Yes, sir.
Yeah, probably I was on this side. So I just wanted to share one information with all of you that how basically this unit architecture and convolutional neural network was very popular also in 2020, and they become the winners in this particular challenge, right? So as there are four individual segmentation tasks for microorganism hemorrhages, software students and hardware students, and the winners were we only using convolutional neural network unit, the variants of the unit architectures, right? You can see only unit architecture. These are the winners, right? I mean, all are using the convolutional neural network or any form of sometimes mask or RCNN and like that. Yeah, so I have shown you only two types of problem statements, and there can be a couple of similar problem statements in case of this. And I mean, by using retinal fundus image, you can detect several other eye conditions like cataract and DME. Also, you can detect myopia, which is very, very important, right? So, I mean, as I mentioned earlier, also, I mean, the kind of methods or the kind of architectures which I've shown can only detect one type of disease. Yes, it can detect binary classification and multi-stage, that is fine, but it can only detect one type of disease at a time, right? So but there is a possibility that one patient may have multiple conditions, as I mentioned. So how to detect multiple eye conditions? For example, I have two fundus images over here, and you can see this particular, the left hand side image, right? The left hand side fundus image, right, carries two important information, so two different types of disease. One is glaucoma and one is AMD, age related macular degeneration. And this particular, the second image over here, right, you can see it basically leads to diabetic retinopathy and cataract together. So now what you have done till now is, let's say, I mean, what is available in the literature is, let's say, for diabetic retinopathy we are having one model, and for cataract we are having another model. So what you can do is, what is the traditional way to solve this problem? Yes, you will pass this image to the DR based model which you have developed. It will tell us whether it is DR or not, but it will again you will pass this image to another kind of model which is dedicatedly designed for cataract, and then it will tell us, yes, whether it is DR and cataract. But you have to also pass through some other models. Let's say for 10 different diseases you have developed 10 different models, and you have to pass these images to 10 different models all the time, and then you have to conclude that, yes, what are the different diseases a person can have. So this is the most difficult part here, that how to detect multiple disease at a time, and this leads to a problem known as multi-level classification problem. At a time, you have to decide, you know, or at a time, there can be multiple eye conditions. You have to decide different class levels. Right? There are a couple of papers, recent papers. Even we've been working on this problem since last 1 year, and we have come up with a few interesting solutions. They are, I mean, under process. I cannot show you those models and all, but if you want to go through this, yes, there are problems related to this. For solving, maybe using natural images, and you can just follow those approaches. You can solve this kind of problem. It's not that easy, because it is even difficult for the doctors to identify the patterns. But yes, we want to mimic the behavior of the ophthalmologist. The ophthalmologist used to also tell us, right, the two things. Yes, the person is having both DR and cataract together. So why can't we develop then a single model to solve the same problem, right? So this is what is the major goal here. Difficult problem, but can be solved. Yes, but the accuracy and the performance which you have got till now is relatively lower, right, compared to the accuracy which you have already got. But for the single eye conditions, because of its inherent complexities of the problem statement. Yes, a couple of couple of other future research directions, use of multimodal imaging. So we met with some of the ophthalmologists recently in some of the hospitals where we are collecting also the data and all, right? So I mean, we also used to discuss with the doctors. So are you only using fundus images to decide or to take the decisions all the time? So they used to tell sometimes no, no. Sometimes we used to also go for fluorescence angiography to get some more information along with the fundus photography. Right, that is also fundus one, but yes, I mean the fluorescence are injected, and then they used to get some clear information from that. And sometimes OCT is very very popular for even glaucoma detection. So why can't we have a multimodal model, right, which will take informations from all these possible types of imaging modalities? But again, for the same patient, you need all the three types of images, right, for that. Yes, it is possible, and it may lead us. I mean, it may lead to also even better decision making because the informations are right combined together, right? And when you are just performing a joint learning kind of things from where the model is learning the representations from the OCT from the fundus photography together, right? So this is also one of the areas which is coming up in this particular research domain where you can work on. And there are a couple of other future directions of research. As I mentioned, that for synthesis, there are very less work has been done till date, where you can just explore this GAN and diffusion kind of models, right? Where other speakers have already mentioned what you mean by GAN and diffusion models. Those can be, applied here to synthesize the high resolution fundus images. And of course, the combinations of the convolutional neural network, VIT together, I've already mentioned why there is a need of combinations of CNN and VIT together to come up with something known as convolutional transformer. Yes, in addition to that, if possible, is there any need of clinical features, right? Clinical features are also very, very important sometimes. So is there any need of clinical features that also we need to explore, right? Also, we need to talk to the ophthalmologist whether you are using any clinical features along with these imaging features to come up with a better decision. That's what also we can do. And as I mentioned already, that yes, we have to also follow some of the you can say the cutting edge learning paradigms like semi-supervised learning, self-supervised learning, right? Maybe other speakers have already mentioned about it and their benefits as well, right? To avoid the problem of basically the annotations, right? Data annotations and labeling, which is very, very difficult, right? So in case of, diabetic retinopathy, I have shown you multiple pathology regions with the annotations and the data labeling of those regions is very, very difficult. And because those are very minute and all, right? So you need at least three, four, or maybe more than five ophthalmologists to finally come up with the final labelings or the final annotation, that kind of things. Okay, here are some of the references. So thank you for your patient listening. So if you are having any queries, so I'll be happy to answer.
Thank you, sir. Participants, if you have any query, you may just write it in your comment box.
So I don't know. I'm not able to see actually open the chat box. If there are any queries, please read it out so that I can, right?
Uh,
I don't know if there is
no, not yet,
something.
sir.
Okay,
Waiting
okay,
for.
because just now we have finished, so we'll wait for 1 2 minutes. They may, right? So they can write because,
Yes.
yeah, yeah.
Participants, you may post your query in the chat box. Sir, are you able to see that
No, no, no,
query?
no. I don't know. There's some problem
So
from.
this one query is on what basis can complexity of CNN be compared with VIT so as to use them together?
Yes, yes. Can you please repeat? Yes.
So basically, she want to ask that on what basis we will be able to compare the complexity of CNN with the VIT
Okay,
so
okay,
that we
got
can
it.
use them together.
So that we can use
Them
together.
together.
Okay, okay, okay.
Yes.
Okay, fine. So yeah, coming to the complexity part, initially when VIT came into the picture, so we've seen that yes, VIT used to take a lot of parameters, right? I mean, basically the number of computations are really high, and because of its self attention mechanism, which takes quadratic complexity. Yes, and there are and multiple times it has been applied to make it multi-head self attention, right? And then the number of parameters goes beyond, right? I mean, it is like beyond sometimes even 100 billion and like that. But we don't have that much of data to apply VIT, right? So what you can do is you can just initially take a lightweight convolutional CNN architecture, which is let's say which takes a lot of less number of parameters, and then you can just use self attentions has been I mean improved over the years to reduce the number of computations, right? So we have also worked upon that. You can read some of our latest papers where we have tried to reduce the number of operations in the self attention, right? Even there are also works available in the literature, so which will also help you in reducing the number of parameters drastically and number of computations as well. That you can do. I mean, you can, I mean, to combine them together, what you can do, as I mentioned earlier, that you can just take a, a pre-trained convolutional neural network architecture followed by some transformer layer, but those transformer layer may contain some of the self-attention block, but those self-attention block are not like the traditional self-attention block. You can just take some of the variant of the self-attention block where the number of computations will be less compared to this. This is how we can reduce. And if you want, because the self attention is mainly focusing on giving us global relationships or global contextual informations, there are also other what I can say alternatives, right, of the self attention through which you can also perform the same, which is known as one of the example is like large kernel attention. Large kernel attention will also help us in reducing the complexity, or you can say the complexity will be reduced from quadratic to linear, right? So if you are using, and that will also help you in capturing the global information similar to the self attentions. There are also other alternatives. If you go through the literature, you will find. I hope that that makes some sense. Yeah, any other questions, Dr. Vikas? Sorry, I'm not able to read. I'm just troubling you. Hmm.
No, sir, that's it. Yes, one more question is there.
Yeah.
The question is, unit is normally used for segmentation.
Yes.
If noisy image is given, can we use unit for image denoising?
Yes, absolutely. A very good question. So yeah, UNet can be used for solving, any kind of problem where you want to generate the image, right? So whenever you need some encoder and decoder kind of architecture, there you can just use the UNet kind of architecture, right? So that means whether it is de-blurring, whether it is denoising. In case of also denoising, you can also use UNet kind of architecture. But you know that where the ground truth will be different, right? In case of segmentation, we need to provide the image along with its corresponding ground truth. So similarly, in case of denoising, the ground truth will be the images. What will be the ground truth? Maybe the input image in this case is a noisy image. So the ground truth will be a filtered image, or you can say clean image. So if you provide the model to this noisy image and the filtered image, or you can say the clean image. So the clean image is like a ground truth for us. This is what we want, right? And there's a noisy image given to us. And then you will just find out the error, I mean the loss, then you will provide this and you will follow the same procedure to solve the problem. Absolutely, you can use this. You will also find a lot of papers on this, right? I mean, how to image restoration using U based, I mean unit based architectures, right? You can say convolutional neural network based architectures, and of course it is unit based because it is very popular. We all know that because of its keep connections. Yeah. Any other questions?
Let me just check, sir.
Yeah, you can refresh and you can just.
Oh, okay, so I think this one was the last one. So no new questions are there.
Okay, no problem. Okay,
So
so
with this,
thank
I
you
think
all.
we are concluding the session. Okay, sir. Thank
Yeah,
you so much, sir.
yeah.
Thank
Thank
you,
you.
participants. We
Yeah,
will leave now.
yeah. Thank you all. Good night. Thank you, Dr. Vikas, for organizing all the
Thank you.
sessions. Thank you.
Thank you. Thank you so much, sir.